With optical multiplexing, it is possible to combine multiple bidirectional signals onto a single fiber. But did you know that it's not possible to do that with signals coming from a coherent transceiver? If you want to find out why, stick around and we'll check it out. So let's start off by talking about the basic working principle of optical multiplexing, which is that we're taking multiple optical signals and combining them by using different wavelengths for each signal. The important part is that at no point can two signals have the same wavelength, otherwise it won't work. Also, it's important to keep in mind we're talking about data transmission. In other words, we're talking about a bidirectional signal. So in other words, we've got a signal going in the one direction and also a signal going in the other direction for the data transmission. In other words, we've got two optical signals. Now, if we have a look at this setup here of a dual fiber WDM, in this case we've got 4 data transmissions, so 4 services. And as you can see in this drawing, we've got both the signals of the one data going in the one direction and the other direction using the same wavelength. But I just said that we can't use the same wavelength. But in this case, it actually doesn't matter because the signals going in the one direction are on the one fiber, and then the signals going in the other direction are on the other fiber. So we've got no conflict. But if we have a look now at a single fiber WDM setup, you will see that we actually need to have different wavelengths for both the transmit and the receive part of each individual data transmission. Now, for non-coherent transceivers, that isn't a problem because the receiver is wideband. In other words, it can receive any wavelength of the respective WDM grid regardless of the wavelength that the transmitter is emitting at. But that's not the case for coherent transceivers, and that's got to do with how the receiver works, because the receiver of a coherent transceiver needs to separate the amplitude, phase, and polarization of the incoming optical signal. Now, the polarization part actually happens here right at the beginning with a so-called polarization splitter. But then we still need to take care of the amplitude and the phase, and that is then done by means of optical heterodyning. And for that, we need a local oscillator, or to put it differently, we need a laser. So how does optical heterodyning work? Well, basically we've got the incoming optical signal, and that is then combined with the signal of the local oscillator onto the photodiode. And the photodiode generates an electrical signal at the difference frequency of both the incoming and the oscillator signal. And the result is the so-called intermediate frequency, which then contains both the amplitude and the phase information, which then the DSP can process. Now, the important thing for the heterodyning to work is that the oscillator frequency actually has to be very similar to that of the incoming signal. Now, a coherent transceiver has already got a laser built in. I mean, we've got the whole transmit part. So instead of adding yet another laser just for the local oscillator, for the optical heterodyning, the transmit laser is used as the local oscillator. And that is then the reason why coherent transceivers actually generally receive at the same frequency as they transmit. Okay, so combining optical signals from coherent transceivers onto a single fiber by means of optical multiplexing doesn't work. So does that mean it's not possible to have single fiber working for coherent signals? Well, no, because there is another passive optical technology that makes that possible. But that's a topic for another Brain Snack video. If you can't wait until then, please don't hesitate to contact us. So, I hope you enjoyed this video and that you learned something today. If so, please leave a comment. And of course, remember to follow our channel so you get your regular dose of Brain Snack. Until next time, bye-bye.